SN1 and E1 reactions, but I want to provide a little bit of framework for this conversation. So what I've drawn out here to the side is substrate, leaving group, solvent, and nucleophile. And I did this because in a previous conversation, we appreciated that there were four main players or four main factors that we need to consider when we're considering whether something's going to undergo a substitution reaction or an elimination reaction. And they are the substrate, the leaving group, the solvent, and the nucleophile. Where the substrate might be something like this, right? Here's the leaving, this is the substrate, right? Here's the leaving group. The solvent we don't draw, right? So sometimes it's easy to overlook it, but you might have the solvent might be water or ethanol or something else, acetonitrile, and the nucleophile, right, is the species that comes in and kicks off the leaving group in an SN2 reaction. In an SN1 reaction, the leaving group leaves first, and then the nucleophile comes in. So these are the substrate, leaving group, solvent, and nucleophile. I want to use those for this conversation. Let's go here now. And let's talk about something. I told you we wouldn't see it a lot, but it is going to happen here in SN1 and SN2 in SN1 and E1 reactions, and that's rearrangements. So, and we're going to focus. I've got this already out here for us. We're going to focus on the substrate for this, right? So, because SN1 and E1 reactions proceed through a carbocation intermediate, right? I don't have one drawn here, but the carbocation intermediate, because that leaves first, right? So, since they go through a carbocation intermediate, the carbocation may rearrange from a 1,2 hydride or a methide shift. So for example, if you have that leaving, I guess I'm going to do this in future slides, but so first of all, when that leaves, you're left with a secondary carbocation, right? Well, if I've got a hydrogen here and it shifts over, then you can see we would be left with a tertiary carbocation, and that's why we get the hydroxide attacking at that position and not with a leaving group left. Okay. So let's talk about that. Here's two. Let's see. Here's two examples of that. But let's move on to the next slide to get more specific on that. Okay. So when a primary substrate is reacted under solvolysis conditions, that is when the solvent is going to be the nucleophile, okay? When a primary substrate, which is what I have here, is reacted under solvolysis conditions, only the product resulting from rearrangement is observed, because you can't, if you have a primary carbocation, right, that's not good, right? So a carbocation intermediate is what would give rise to, a primary carbocation intermediate was what would give rise to this product, but it's not observed, right? Because you get the shift. Remember, primary carbocations are too unstable to form. We're not going to see those. So in this case, the rearrangement occurs as the leaving group leaves. All right, and here's the mechanism for that. You see, I've got that already. Here's the mechanism for that. The leaving group leaves. And as it happens, so this is kind of like a concerted mechanism, right? It is concerted. It happens at the same time. The methide shifts over, and the leaving group leaves. And then you're left with a tertiary carbocation intermediate, which is A-OK. All right? So then you get the nucleophile comes in, which is the solvent molecule. It acts as a nucleophile. That's why we call it solvolysis. The nucleophile comes in, and then it's deprotonated, right? Proton transfer. Okay? Now let's talk about the solvent. So experimental data indicates that SN1 and E1 reactions are faster in a polar protic solvent. And a protic solvent, recall, is something that has a hydrogen that's bonded to an electronegative element, right? So those three are protic solvents, okay? And it's called protic because the hydrogen is bonded to an electronegative element. They are polar protic. All protic solvents are polar. Look here, in SN1-E1 reactions, look at that. Look how much faster. The relative rate is 45:1 compared to, wow, 5/1000ths. Okay, so this is a substantially faster if it's a polar protic solvent. And just a comment about the dielectric constant, it turns out it doesn't so much matter that how polar they are as much as the big difference comes from the fact that they're protic. Okay, and here's the reason why. So the reason why it's protic is because an aprotic solvent the Protic solvent stabilizes the nucleophile. So you see how low in energy the nucleophile is here? So if the nucleophile is stabled, it is, if the I lost my head. Let me go back here. I was pointing the wrong thing. So do you see how low in energy, how stable these starting materials are, right? Because the Protic solvent stabilizes the nucleophile. But the aprotic solvent does not stabilize the nucleophile. This comes from a previous conversation, SN2 conversation, remember that? So the aprotic does not stabilize the nucleophile, and so consequently, the activation energy is much lower than this activation energy, right? Okay. Now, the nucleophile is not, remember for an SN2, the rate is equal to K substrate nucleophile, right? This is SN2, but in SN1, the substrate is the rate limiting step. So the stability of the nucleophile doesn't matter as much. All right. So consequently, the fact that Protic solvents stabilize the carbocation intermediate better, they stabilize the result of this better, then it turns out we get a faster reaction with a Protic solvent. Okay? Let's move on now to the leaving group. The better the leaving group, the faster the SN1 or E1 reaction, of course, right? Because if we've got a leaving group here, and that is the rate limiting step, well, the more stable the leaving group is on its own, right? The more stable it is on its own, the faster this is going to happen. So remember, the rate limiting step is SN1, for SN1 and E1, is the ionization step, which is what we're talking about here. This is plus, I didn't draw that out. Oops, that's a secondary. So here's a secondary, right? And since here's our carbocation intermediate, so since our carbocation intermediate since the formation of the carbocation intermediate is the rate limiting step, then the quality of the leaving group substantially increases or scales with the speed of this reaction. Okay? Now let's talk about the substrate again. The more stable the carbocation intermediate, the faster this will be. So remember that a tertiary carbocation is more stable than a secondary carbocation, and we're not going to see a primary carbocation, right? So solvolysis reactions of primary and secondary are often too slow to observe the formation of SN1 and E1 products. So if you see a primary or secondary alkyl halide, you should be thinking not SN1 or not E1. If you see a tertiary, you know this is not going to go SN2. Not going to go SN2. SN2, right? It's not going to go SN2. And so with a tertiary alkyl halide, you can expect that you'll see SN1 and or E1 products. Now benzylic, that is a carbocation, which is, you see this looks like a primary carbocation, but it's stabilized by resonance, right? So a benzylic carbocation has similar reactivity to a tertiary, and allylic for the same reason, right? This undergoes resonance. Resonance, right? That's an S. Resonance. Both of these undergo resonance, and so those will undergo solvolysis in a fashion similar to tertiary carbocations. Okay, you should be able to judge whether or not an alkyl halide will undergo SN1 or solvolysis via SN1 or E1 reactions, and based upon comments which I said in the previous slide. But again, you should be making notes about these things and practicing. Primary and secondary are not going to undergo solvolysis, and tertiaries will. Okay, tertiary allylic and benzylic alkyl halides will undergo solvolysis to give a mixture of SN1 and E1 products. Where was I on that? Let me go back up here. To give a mixture of SN1 and E1 products. Okay, like we saw with E2 eliminations, it's possible to get E1 eliminations to yield more than one regioisomer. So, for example, if we have, so you've got a tertiary alkyl halide here, okay? If this chloride leaves, let me draw a nicer arrow here. Let me get rid of that circle. If this chloride leaves, Okay, you're going to have a tertiary carbocation, right? And so the question is, when a base comes in, is it going to abstract this proton for the Zaitsev product, or is it going to abstract, I'm sorry, for the Hofmann product, or is it going to abstract this proton for the Zaitsev product, right? Here's the Zaitsev product, here's the Hofmann product, okay? Here's the Hofmann product, and you also can get some substitution product, okay? E1 reactions will always give the most stable alkene. That's nice to know. E1 reactions will always give the most stable alkene. Which one of these is the most stable? It's the most substituted, okay? So we're mostly not going to see that. All right, this will be your major product for E1. So E1 reactions are regioselective, but we cannot control the regioselectivity like we can with E2. Remember, with E2, we could get some of the Hofmann product if we used different bases. Okay, further, it's further possible to obtain several alkene stereoisomers in E1 reaction as the following. So these two, right, you can imagine that with E1, we have both the, let's see, what's this? This is the E, here's the Z, right? And here's a Hofmann product, Hofmann, okay? But this is going to be the major product because it is the most stable, okay? It still is going to give the most stable. And so we can say that E1 reactions are stereoselective. But you have to realize that it is likely that we're going to get a mixture of things, okay? Okay, so when the alpha carbon is in an SN1 reaction, it's chiral. Okay, so we have here's our alpha carbon right here, and we have a chiral substrate. We can obtain two substitution products that have opposite configurations at the reactive carbon. Now SN2 has a backside attack, right? And only inversion of configuration is obtained. Okay, so you're going to get a backside attack that is the part that the bromide's leaving. The nucleophile is going to be coming in from the opposite side. Okay, but that's not the case with SN1. However, we still get more of the inversion product observed because it's not unusual to have a nucleophile sort of waiting in the wings as the leaving group is leaving. Okay, so that's a pretty fast flyover. We focused on substrate, we focused on leaving group, and we focused on solvent. We didn't say anything about nucleophile. Why is that? Well, I guess I said something about it here, but mostly we didn't address the nucleophile. Why is that? Well, because again, this is a unimolecular reaction, and it's primarily these are the only three things that are around when we're considering the rate limiting step. Okay, hope that's helpful. Go practice. Good luck.